Welcome back, geology fans. Through these episodes on the history of plate tectonics, we've repeatedly pointed out all the earth-building activity that takes place at these plate boundaries. Today we focus on these boundaries, what are their major categories, and emphasize what stresses, processes, and features you might expect at each. To start, you can think of three basic movements that two plates can have relative to each other. We could pull the plates apart, in which case we call the jagged line between the plates a divergent boundary. We could push the plates together, in which case we call it a convergent boundary. With convergent boundaries, we will have to be more specific as to what type of lithosphere, ocean or continental, is running into what other type of lithosphere. Lastly, we have the case where one lithospheric plate grinds past another plate without pushing together nor pulling apart, just sliding sideways past the other. These are called transform boundaries, but your instructor is doing his best to push the term conservative boundaries so we can reserve transform for the multifarious sideways motions, whether they be on-plate boundaries or not. Let's start with divergent boundaries, the places where plates pull apart. Every ocean ridge is a divergent boundary, pulling apart, but constantly being refilled by upwelling asthenospheric material leading to generally basaltic volcanic action. Folding is relatively absent, but features such as normal faults and boudinage, to be discussed at a later episode, are more common. We see a downdrop valley at the center bounded by these normal faults, along which a majority of the new intrusive and volcanic igneous activity is taking place. In a sense, this mid-ocean ridge connects into a web around the world, making the longest low mountain chain on our planet. The mid-ocean ridge rises from the average abyssal plain depth of 4 to 5 kilometers below sea level to a peak averaging 2.5 kilometers below, and occasionally making it up to the surface in places like Iceland. In Iceland, you can stand with one foot on the Eurasian plate and the other on the American plate, with your feet spreading apart at an average of a few centimeters per year, or about the rate your fingernails grow. Iceland is like the seafloor come to the surface, but there have been, and are today, places on Earth where it is under a continent that this rifting is taking place. On a continent, a rift is a scar in the land where both sides are pulling away from each other with a normal fault-bounded downdrop block in the center. We know from the history of supercontinents forming and breaking apart that continents can rift apart completely, but there are places on Earth where rifting started but was never able to get the impetus to rip the land fully apart. In the Earth and Environmental Systems podcast, I emphasize the strange fact that nature loves 120 degrees. If you look around, you'll see it comes into play in the skin of pineapples, the connection points of bubbles, and the honeycombs of bees. Here we find that when continents begin to break apart as a newly forming divergent boundary, it tends to happen with 3 cracks at 120 degrees from each other. If we think about the asthenosphere below, we can imagine 2 of these 3 cracks opening and straightening out, but the third being abandoned and failing to fully rift apart. The Rio Grande Rift is an example of such a failed rifting on a continent, as are many other downdrop crustal blocks of major river systems on continents. It just so happens that the modern world has one of these continental divergent boundaries forming, and we can travel there with ease on Google Earth. The view over Arabia and Northeast Africa reveals an obvious 120-degree feature in the Gulf of Aden, the Red Sea, and this scar running down eastern Africa called the East African Rift. Eventually, the 2 seas will open up, taking Africa away from Arabia, but failing to break off on its eastern side as the East African Rift fails. Currently, the East African Rift is still active as volcanic eruptions and earthquakes continue to force landmarks on either side to move away from each other. But past evidence shows this is going to be what we call an allocogen, a failed rift that does not open up fully to form new ocean floor, but the other 2 breaks are doing just that. The Red Sea and Gulf of Aden are now new ocean floor. Eventually, all divergent boundaries that don't become a failed allocogen become a mid-ocean ridge, which is, by definition, a plate boundary, a divergent plate boundary. The volcanoes are basaltic in chemistry, and the earthquakes are relatively weak and shallow. The next boundary type would be when one plate moves toward another, causing compressive stresses in what is known as a convergent boundary. With divergent boundaries, we had to distinguish divergence below continents from the fully formed mid-ocean ridges, but convergent boundaries come in 3 different flavors depending on what 2 types of lithosphere are coming together. If you converge ocean lithosphere with ocean lithosphere, both are of equal density and thus equally likely to subduct into the mantle. But once there is a loser, it tends to continue to lose and subduct and be recycled. This is an ocean-ocean convergent boundary, which shows an oceanic trench over 5 kilometers deep and up to 11 kilometers deep. There is enough silica-rich sediment being taken down here along with water to form magma that rises to the surface again under the overriding plate to form an arc of andesitic volcanic islands. The Aleutian Islands are an example of ocean-ocean convergence leading to a volcanic island arc. The earthquakes start shallow at the trench and get deeper under the overriding plate that has the volcanic island arc in a Wadati-Benioff zone of earthquakes. Some of these deep focus earthquakes are some of the strongest earthquakes humanity endures. This earthquake pattern is the same as the next type of convergent boundary, Oceancontinent Convergence. Here we know which plate will subduct, as ocean lithosphere is denser and thinner than continental lithosphere, which is simply too buoyant to subduct into the mantle. The ocean plate loses, though sometimes it can leave a chunk behind stuck to the edge of a continent, which we call an ophiolite sequence. But once the ocean crust is subducting, we again form a trench with shallow earthquakes at the trench getting deeper below the continental plate. As with the ocean-ocean convergence, we take down enough water-laden felsic chemistry sediment to cross the solidus line and produce magma, which can rise to make an arc of andesitic to felsic volcanoes on land. The closest example to me in the United States is the Juan de Fuca oceanic lithosphere subducting below the North American plate from northern California up through Washington state. The Cascade Range of volcanoes, Mount Shasta, Mount Rainier, Mount St. Helens, are all volcanoes along this ocean-continent convergent boundary. Though the area around the trench sees a lot of compressive stress, which can lead to reverse and thrust faults and folds, farther away from the trench itself, you start seeing the effect of trench suction, where eddies in the asthenosphere pull back towards the trench. Tension resulting in normal faulting can occur in this back arc basin, and its subsidence can create a surface basin to accumulate sediment and ash from the volcanic highlands. The last convergent boundary type is the continent-continent convergence. We can imagine this starts as an ocean-continent convergence until the continental shelves meet each other. As already stated, continental crust is too low density to subduct into the mantle, and so unlike the ocean-ocean or ocean-continent convergence, where the compressive stress can be released by deforming the subducting slab and letting it slip down to its destruction, with continent-continent convergence, all the compressive stress has to go into deforming the continental edges, with reverse and thrust faults, folding, and large-scale uplifted mountain belts. The Himalayan mountains and plateau are an example of a continent-continent convergence as the Indian plate continues to slide into the Eurasian plate, lifting the Himalayas and squeezing out the Sinai Peninsula to the east. The majority of great mountain belts of the world are due to continent-continent convergence, though one of the great plate tectonic anomalies is in my backyard in the Rocky Mountain system, which sits not at the edge of a continent, but in its interior. After much head-scratching on this apparent anomaly, evidence now leads to the idea of a shallow subducting slab which was able to slide below western North America until it got stuck around the central western United States and caused the Rocky Mountains to buckle and rise. So my local mountains are not a continent-continent convergent boundary like the Himalayas, Appalachians, Urals, or Alps, but all are compressive, resulting in crustal shortening, and this varied deformation of varied depths and materials leads to all kinds of volcanism, all the way from basaltic to felsic. The Arbuckle Mountains in Oklahoma are hardly mountains anymore, as they are the result of long past continent-continent collision with Africa and have worn down by erosion to these lower hills today. Meanwhile, the Himalayas are still active, with India continuing to slide north into Eurasia and the mountain range continuing to be forced upward. The final plate boundary type does not have the plates pushing together like the converging boundaries, nor pulling apart in the divergent boundaries. Rather, we see two plates slide past each other, neither creating nor destroying crust and lithosphere to any significant extent. Traditionally, these are called transform boundaries, though this instructor prefers to call these conservative boundaries and reserve the term transform for the transform faults. Conservative boundaries conserve their lithosphere as they slide by each other with tremendous friction and shear stress at their edges. It is common to see offset features across such a boundary, such as offset streams that look as though they are slowly being pulled apart. Even human features like fences or roads can get offset if they lay across such a boundary. Since there is one of two possible movements on such a fault line, we speak of these as either being right lateral fault breaks or left lateral fault breaks. This is a right lateral fault, as no matter which side one stands on facing the fault, the other side is moving to one's right. In a left lateral fault, you would see the other side going to your left as you face the fault line. Since faults are rarely perfectly straight, these horizontal shifts sometimes open up holes called sag ponds, or buckle up modest mountains as the fault bends the other way. The closest example of a conservative boundary to me is the San Andreas Fault along the western edge of the United States, mostly through California. This is a right lateral motion with LA on the Pacific Plate moving northward towards San Francisco, which is barely on the North American Plate. So the two major West Coast cities are slowly approaching each other. We see that Turkey is similarly getting torn through. Earthquakes on these conservative boundaries are more common than other places, but can be shallow to intermediate in depth, and in some cases build up enough energy to do significant damage. Volcanoes are not really that common, though. What is common along these conservative boundaries is fault melange, a really messed up rock that has been slowly ground between two lithospheric plates. Before leaving plate boundaries altogether, it is interesting to note that there are several places on Earth where we don't just get two plates meeting, but three. These triple junctions can involve divergent rifts, convergent trenches, and transforming conservative boundaries, and in some interesting combinations. The East African Rift is part of the Afar Triangle, which is technically a ridge-ridge-ridge triple junction until the East African Locogen fails. Off the western coast of the United States, the San Andreas eventually runs into another triple junction with the Juan de Fuca plate, with transformed trench triple junction action. The Baso triple junction off Japan's coast is a triple trench system, while just back on land there is another triple junction around Mount Fuji. All these plate boundaries and junctions have to conserve mass in the end, and one can imagine great events possibly having worldwide effects through plate tectonics. It is interesting to note that India first touched Eurasia around 40 million years ago, and went into compressive mountain building over subduction starting at that time. Meanwhile, it is interesting to note the large hotspot or mantle plume beneath the Hawaiian Islands. We mentioned before these hot spots act like stationary pens as the plate moves over them, and so we see the record of movement of the Pacific Plate from this line going from active and above water to all extinct and submerged volcanoes. As these are all basaltic, the rock is easily dated, and we find the youngest islands are those still active, and the farther north we go, the older the islands get. And then we hit this inflection point. It appears that for a long time the Pacific Plate was going in a mostly northerly direction, but then shifted off to its present course of northwest. This kink point, the change in direction, took place 40 million years ago, about when India ran into Eurasia and got stuck. Is it too hard to imagine all or more than one or two plates having to readjust to a new movement paradigm? May I suggest at this point that you too take a new tack on this subject and jump away from the Earth Explorations video series for a moment and go over to iTunes U and search for Blakey, B-L-A-K-E-Y. Click on Campus Lectures for the Colorado School of Mines, and then choose Ron Blakey, Paleogeography and Paleotectonics of the Western North American Continent. With the lessons you've received here, you are now prepared to understand the story Dr. Blakey tells there, and learn how he made the famous maps you've seen through this series and in many other venues. Once you've absorbed that resource, come back for our next episode, as we delve into some of the details of those earthquakes we've mentioned so much of today, here on Earth Explorations.